Okay, let's get started. So this is day 8. Today we're going to be talking about limiting and excess reactants. Before we get started, I just want to remind you that I'm posting the solutions for all of the problem sets as we go along. So I definitely recommend going and doing a quick check of your work just to make sure you understand where those answers come from. And you're always welcome to stay after class if you have questions, go to office hours with the tutors or email me or use the B courses discussion. So please ask for help if you're confused. So I just wanted to do a quick summary of how we got to this point since we're a little past halfway. So the first day we just did intro. The second day we talked about converting units in general, and that will come in later with moles. And then day 3, we talked about atoms. So what are atoms made of? Protons, neutrons, electrons, the structure of atoms, and how to figure out how many protons, neutrons, and electrons an atom has from the periodic table. Day 4, we focused on electrons. So valence electrons, Lewis structures, orbitals, all of that. Day 5, we talked about bonding and drawing molecules. So this is where we first introduced those pesky line drawings. And then day 6, we talked about counting molecules. So lots of molar mass and moles. And then yesterday we talked about reactions and stoichiometry. So just wanted to highlight this list really quick, just so you know which videos you can go to if there's something you're confused on or anything like that. So I hope you can see how this all kind of builds on each other and we end up with these chemical reactions and stoichiometry. And today we're going to talk about how we can use these stoichiometric coefficients. There's a question in the chat about organic chemistry. Organic chemistry is really just chemistry, but focusing on molecules that are mostly made of carbon, hydrogen, oxygen, and maybe some nitrogen. So a lot of what we're doing is relevant to organic chemistry. So we're not going to like specifically dive into OChem, but you do need to understand like these reactions in stoichiometry to go into the specifics that are covered in organic chemistry. So we're not going to focus on line drawings today, but there's plenty of practice. And if you're still confused on those, absolutely, you can stay out after class and we'll talk about it. Is organic chemistry as complex as people say? I loved organic chemistry. That was one of my favorite classes in undergrad. I thought it was really fun. I found that to me, there wasn't a lot of memorization. It was a lot of sort of logic and understanding how to interpret different things. So to me, it felt like fun puzzles. So I loved it. Some people hate it. For any class that exists, you'll find people that love it and people that find it really difficult. I liked it a lot, and I don't think you should be scared of it if you're interested in it. So today we're going to dive deeper into reactions. So just as a review, we write our reactions as going from reactants to products. So reactants are what we start with, they react, and then the reaction happens and we end up with our products. Stoichiometric coefficients that we get by balancing our reactions tell us the ratio of the different molecules. So for example, if I have a reaction that's 2A plus B goes to C, this is a really common way of writing reactions especially in engineering. So A, B, and C are all molecules. They could be, C6H12, CO2, whatever. And we're just being lazy and saying, we don't want you to focus on the specific atoms and bonds. A is just something, B is something else, and C is something else. So this lets us just sort of, instead of writing C12H17O4 forever, it just lets us simplify it. So you'll probably see that a lot, especially in your engineering classes. So I just want to get you used to that. So if I have this reaction that's 2A plus B goes to C, then that means that 2 molecules of A react with 1 molecule of B to give 1 molecule of C. So if I want 1 molecule of C, I need 2 molecules of A and 1 molecule of B. And as a reminder, moles are a count of the number of molecules. So 1 mole is just 6.022 times 10 to the 23rd molecules. So if I want 1 mole of C, then I need 2 moles of A and 1 mole of B. Questions on this? So our stoichiometric coefficients we're just using as a ratio to tell us how many of each type of molecule we need in our reaction. So to make sort of a day-to-day analogy, if I'm making a sandwich, I need 2 slices of bread and 1 slice of cheese, whatever. It's just telling us how much of each type of thing we need to make whatever we want to make. Okay. So we're going to talk about what quantities are conserved and what are not, and I'll talk about what that means. So I'm taking this reaction as an example. So I have 2H2 plus O2 goes to 2H2O. So you'll notice that I have balanced this reaction already. I have 4 hydrogen atoms on the left and 4 on the right, and 2 oxygen atoms on the left and 2 on the right. I'm going to sound like a broken record today, but please don't ever do anything without balancing your reaction first. Once you get a lot of practice with balancing, it'll take you 5 seconds to check whether your reaction is balanced. So it's always worth doing. It's a very easy way to do a ton of work later in your problem and have it be completely wrong if your reaction is not balanced. So I want you to go into groups and discuss whether mass, atoms of each element, total number of atoms, and total number of moles will be conserved. And so what that means is, as I'm running this reaction, if I start with 100 grams of stuff, will I always have 100 grams of stuff as the reaction proceeds? If I start with 4 atoms of hydrogen, will there always be 4 atoms of hydrogen as the reaction proceeds? If I start with 6 total atoms, will there always be 6 total atoms? And if I start with 10 total moles of stuff, will there always be 10 total moles of stuff as my reaction proceeds? Does anyone have any questions about what conserved quantities mean and what I want you to be discussing? So I'm going to send you into groups to discuss this. And I'm going to poll you when you get back. So I hope that you will discuss it, kind of come to a consensus in your group. I'll give you like 3 minutes. So I'll pull you back in at 10:51 or so. Okay. So go ahead and accept those breakout room invitations. Okay, so accept those invitations if you haven't already. I'm going to pause the recording. Those of you watching this later, I'd recommend you pause and think about it. Okay, so sorry, I forgot to hit record. So just very quickly, mass is always conserved, always, no matter what. And then the atoms of each element and the total number of atoms is also always going to be conserved because we're not messing with the nucleus. So if we have 4 hydrogens and 2 oxygens on the left, we're going to have 4 hydrogens and 2 oxygens on the right. So any questions on those first 3? Okay, so the last one is the one that you guys were kind of 50-50 on. So moles are not conserved. We started out with 2 moles of H2 and 1 mole of oxygen. So that's 3 moles of total molecules. And then we're ending on the right with 2 moles of H2O. So we're starting out with more moles of stuff than we're finishing with. And that's because moles are a count of molecules, not a count of the atoms or a count of the mass. So going back to like our sandwich analogy, if I start with 2 pieces of bread and 1 piece of cheese, you can think of that as 3 things. And then I'm ending with 1 sandwich. That's 1 thing. And so you can think of moles like that as a count of stuff. And so moles are not conserved. Does this make sense? Okay. So this means that there's like different times that we want to use mass and different times that we want to use moles. If someone says, I start out with 10 moles of stuff, how many moles of stuff do I end with? That's hard. Only mass is conserved. But if someone says, here's my reaction, it's 2H2 plus O2 goes to 2H2O, I use up 5 moles of H2, how much H2O can I make? Then you need those stoichiometric coefficients, so you need moles. So we're going to spend the rest of the day using that. So this is how we're going to use it. So again, sorry, I know I'm a broken record. This reaction is balanced. I cannot do anything using stoichiometric coefficients until I have checked that my reaction is balanced. So stoichiometric coefficients tell us the ratio of different molecules or moles of those molecules in a reaction. So let's say that I want to produce 6 moles of H2O. How many moles of H2 do I need? And how many moles of O2 do I need? So with this simple example, you might be able to just look at the stoichiometric coefficients and kind of figure it out intuitively, but I want to formalize it a little bit. So I want an answer in units of moles of H2. So I'm going to say I want 6 moles of H2O, and then I'm using these stoichiometric coefficients like a unit conversion. So for every 2 moles of H2 that I use, I make 2 moles of H2O. So those 2s are just my stoichiometric coefficients. So for every 2 moles of H2 that I use, I make 2 moles of H2O. And now, just like I always do with my unit conversions, my moles of H2O can cancel out, and I'll end up in units of H2, of moles of H2. So in order to make 6 moles of H2O, I need 6 moles of H2. So I can do exactly the same thing with oxygen. I want to make 6 moles of H2O. And from my stoichiometric coefficients, I use up 1 mole of O2 every time I make 2 moles of H2O. So I need 6 divided by 2 is 3 moles of O2. Questions on this?
Can you kind of show like how to do it? Because the way I'm seeing it is like you cancel out the bottom, right? And
Yep.
you're left with 2 times 6, right?
Yeah, so on the, for the first one, my units are going to cancel out, and I do 6 times 2 divided by 2 is 6. And for the second one,
they keep the 2.
Yep, so for the second one, my units of moles of H2O cancel out. So I do 6 times 1 over 2 is 3. Does that help?
Yeah, okay, cool, yeah.
Okay, did I see another hand? Okay. Yeah, I see a hand.
Yeah, I was trying to ask, why did you do 2 moles of H2 over 2 moles of H2O? Like, wouldn't it be just 1 mole of H2 over 1 mole of H2O? Or
yeah, so that would be the same thing. 2 over 2 is 1 over 1. All I'm doing is explicitly using the stoichiometric coefficients. So if it's easy for you to see, I need the same number of moles of H2O as the same number of moles of H2, so I need 6. That's fine, that's correct. I'm just kind of trying to show you explicitly that these stoichiometric coefficients are a ratio. So for every 2 moles of H2O that I make, I need to use up 2 moles of H2. That is, like you said, that's exactly the same as saying that for every 1 mole of H2O I make, I need 1 mole of H2. So those 2's are going to cancel out, which is why we get 6 and 6. But I'm just kind of showing you that you don't have to think about that. You can just straight up take the stoichiometric coefficients and use them as a ratio. Does that make sense?
Yeah, thank you.
Okay. So that's how I do it if it's in moles. If it's in mass, I'm asking the same question. Let's say that I want to produce 36 grams of H2O. How many grams of H2 do I need and how many grams of O2 do I need? So you might, by instinct, want to do the same thing that we did before and say that I need the same amount of H2 that I need of H2O. So I need 36 grams and I need the same amount. I need half the amount of H2O that I need of O2. And that would get me 18. This is wrong. A very quick check of this, of why this is wrong, is you can check whether mass is conserved. So I'm starting with 36 plus 18 grams of stuff, and I'm ending with 36 grams of stuff. That's not possible. That would mean that I've just lost 18 grams of stuff. So I have to convert to moles before I can use those stoichiometric coefficients. So I'm going to go through kind of fast in one step how to do it on this slide, but I'll break it down into many steps on the next slide. So what we need to do is take our 36 grams of H2O, convert it to moles of H2O using the molar mass. So the molar mass of H2O is 18 grams per mole. Then we use our same stoichiometric coefficient conversion that we had up here. And then the molar mass of H2 is 2 grams per mole, so we get 4. So we can do the same thing with O2. We're converting our H2O to mass using our stoichiometric coefficients to convert between moles of H2O and moles of O2, and then converting back to mass of O2. So again, I know this is really quick. I'm going to break it down into more steps on the next slide, but I just want to point out here that now this works because my mass is conserved. I'm starting out with 32 grams of O2 and 4 grams of H2, so that's 36 grams of stuff, and I'm ending with 36 grams of stuff. So a really good check, if you're ever doing a problem and you find that your answer implies that mass is not conserved, something has gone horribly wrong. You have made a mistake. This is not possible. So we're going to break down step by step how to do this. But the point that I want you to take away from this slide is that if you want to use stoichiometric coefficients as a ratio between your two different reactants or products or whatever, you need to convert to moles. Those stoichiometric coefficients only apply to moles. That's why this unit conversion is in moles of H2 over moles of H2O. So questions conceptually on why I'm doing this or how I'm doing this? Okay. So I'm going to give you an example, and then I'm going to have you do a similar example in your groups. So let's take this reaction. So solid aluminum reacts with gaseous chlorine, Cl2, to make AlCl3. So the problem statement, the question that I want to answer is, if I have 535 grams of Cl2 and an infinite amount of aluminum. So all I mean by that is I'm never going to run out of aluminum. How much AlCl3 can I make if I use up all of my Cl2? So I don't have to worry about running out of aluminum. I'm only going to run out of chlorine. So if I use up all my chlorine, how much AlCl3 can I make? Does everyone understand the question? So I'm just worrying about, if I use up all my chlorine, how much AlCl3 can I make? So step one is always balance the reaction. Right now I have 2 chlorines on the left and 3 on the right. This is not allowed. Don't do it. So I'm going to balance my reaction. And what I'm going to get is 2 aluminums plus 3 chlorine gas molecules makes 2 AlCl3. So now I have stoichiometric coefficients that are right and that I'm allowed to use. So I want to know how much AlCl3 can I make if I use up 535 grams of Cl2. So the first thing I'm going to do is convert to moles. So from the periodic table, I know that the atomic mass of 1 atom of chlorine is 35.45. So the molar mass of Cl2 is 70.9 grams per mole. And then I can just convert my 535 grams of Cl2 to moles using that molar mass. And so I'm starting with 7.55 moles of Cl2. Then I can use my stoichiometric coefficients. So I know that for every 3 moles of Cl2 that I use up, I'm going to make 2 moles of AlCl3. So I can cancel out these moles of Cl2, and I can do 7.55 times 2 divided by 3, and I will make 5.03 moles of AlCl3. And then the last thing I need to do is I asked how many grams of AlCl3 can I make? So I just have to convert 5.03 moles to grams. So I looked up the molar mass of AlCl3 using the periodic table. 5.03 moles of AlCl3 times 133.34 grams of AlCl3 per mole gets me 671 grams of AlCl3. So that means that if I use up 535 grams of chlorine, I can make 671 grams of AlCl3. Does anyone have any questions on how I did this?
How would this problem be different if there wasn't an infinite amount of aluminum?
Great question. That will be what we do in the second half of the class. So if there was a finite amount of aluminum, but an infinite amount of chlorine, then it would be exactly the same. That's what you're going to do on the next slide, is you're just switching. I'm going to use up all my aluminum. If there's a finite amount of both, you have to figure out which of those is important. And we'll talk about that in a minute. So I will come back to that question in 10 minutes. But that is a very relevant question. Good job.
Where did the 133.34 grams come from?
That's just the molar mass of AlCl3. So I looked on the periodic table. I found the molar mass of aluminum, the molar mass of chlorine, and I just added them up like you did on the past homework when you're figuring out the molar mass. Does that make sense?
Yeah, thank you.
Yeah, so yes, you will always need to be comfortable using the periodic table to figure out the molar mass of your different compounds so that you can convert between grams and moles. So today, I'm going to do that part for you, just so we can focus on this, but definitely you'll need those skills of converting between moles and mass. Any other questions on how I did this? Okay. So I'm going to have you practice this exact same reaction. I have 255 grams of aluminum and an infinite amount of chlorine. So what that means is I'm never going to run out of chlorine. I'm just going to use up all my aluminum. How many grams of AlCl3 can I make? And so based on that exact question, so good job, I've given you the molar mass of aluminum and the molar mass of AlCl3. So you should be able to find those on the periodic table. So you should be able to figure these out. I just wanted to save you a couple minutes so we can focus on the actual question at hand. So you're going to do exactly the same thing I did on the previous slide. except now I'm using up all my aluminum. Does anyone have any questions on what I want you to do? Okay, I'm going to give you until about 11:20. And I'm going to pause the recording. And if you're watching this later, I would definitely recommend that you pause and practice with this. Okay, I'm just going to give people 10 seconds to finish coming back in. Okay, so I'm going to follow exactly the same steps that I followed on the previous slide. The first step is always to balance the reaction. And then we're going to convert our 255 grams of aluminum to moles, use our stoichiometric coefficients, and then convert back to mass. So we're going to balance our reaction. It's the same as it was before. So I've done that step for you on the previous slide. Then I have 255 grams of aluminum. And that's the only thing that's going to matter because I'm never going to run out of chlorine. So the first thing I'm going to do is convert my aluminum to moles. So I have 255 grams of aluminum, and 1 mole of aluminum weighs 26.98 grams. So that means I have 9.45 moles of aluminum. And then I'm going to use my stoichiometric coefficients from my balanced reaction. So for every 2 moles of aluminum I use up, I make 2 moles of AlCl3. So I'm going to do 9.45 moles of aluminum times 2 moles of AlCl3 per 2 moles of aluminum. And so that means I'm going to make 9.45 moles of AlCl3. And then the last thing I need to do is convert those 9.45 moles to mass. So 9.45 moles of AlCl3 times 133.34 grams of AlCl3 per mole means that I can make 1,260 grams of AlCl3 in this case. Does this make sense? Does anyone have any questions on how I did this? We'll talk about why you should care in a minute and why this is important, but does this conceptually make sense? So how did I get the 133.34? That's just from the periodic table. So I looked at the mass of aluminum. It's 26.98 on the periodic table. Chlorine is 35.45. So I did 26.98 plus 3 times 35.45, and that's how I got my molar mass. So the third step is we're just using our stoichiometric coefficients and converting from moles of aluminum to moles of AlCl3. So in this case, those 2 stoichiometric coefficients are the same. So if I use up 9.45 moles of aluminum, I'm going to get 9.45 moles of AlCl3. But on the previous slide, if I can go back, those stoichiometric coefficients were different. And so I had to use the 2 and the 3, and so I got a different number. So it just so happens that in this case, those stoichiometric coefficients are the same. The person in the chat with the math question, I think you just did 225 instead of 255. The only reason we multiplied the mass of chlorine by 2 was that it's Cl2. It's 2 atoms of chlorine per molecule of chlorine. But for aluminum, it's just aluminum. So the molar mass of aluminum is just 26.98. So these 2s are different. So this 2 means there's 2 atoms of chlorine per molecule of Cl2, but this 2 is a stoichiometric coefficient. So this 2 came in this ratio of stoichiometric coefficients here, not in the molar mass. So the 2 that's in the molecule tells us what the molecule is made of. And the number that's in front of the molecule is the stoichiometric coefficient that tells us how many of those molecules we need. Okay, so now we're going to get to the question about what happens if I don't have an infinite amount of either of these things. And that's where what's called the limiting reactant comes in. So the limiting reactant is just which one will run out first. Which reactant limits how much product we are able to make. So for example, let's say I have a reaction that's 2A plus B makes C. So again, A and B and C are just molecules of some kind. I don't care, it doesn't matter. I have 5 moles of A and 2 moles of B. What is my limiting reactant? So let's just draw it out. I have 5 moles of A. So I have 5 units of A molecules, and I have 2 moles of B. In order to make 1 mole of C, I'm going to use up 2 moles of A and 1 mole of B. To make another mole of C, I'm going to use up 2 moles of A and 1 mole of B. Now I'm totally out of B. So even though I have A left over, I cannot make any more B. Sorry, I cannot make any more C because I've used up all of my B. So B is my limiting reactant. Does that make sense conceptually on what a limiting reactant is? So the limiting reactant is what limits how much product I can make. So if I had 500 moles of A, it wouldn't matter. If I only have 2 moles of B, I can only make 2 moles of C. So if I want to make more C, what I need to do is get more B. B is what's limiting what I can do. So the reactant or reactants that are not limiting are called our excess reactants. I have extra of them left over once I run out of my limiting reactant. So just a word that you should recognize, if A and B run out together, they're in what's called a stoichiometric ratio, and neither of them is limiting. So if I had 4 moles of A and 2 moles of B, they would both run out at the same time. Normally, that's not the case. Normally, I have something is limiting and something is excess. So in our example that we were solving before that you worked on in your groups, where this is my reaction, if I have 535 grams of chlorine and 255 grams of aluminum, which one is limiting? And so the way that I'm going to solve this is I'm going to use the steps that we did on the previous slide. So we already figured out that if I had 535 grams of chlorine and an infinite amount of aluminum, so I'm assuming that chlorine was limiting, I found that I could make 671 grams of AlCl3. If I went the other way and I had 255 grams of aluminum and an infinite amount of chlorine, I found that I could make 1,260 grams of AlCl3. So 671 is less. So as I'm proceeding in my reaction, once I've made 671 grams of AlCl3, I will have totally run out of chlorine. So I can't make any more AlCl3 because I will never get to 1260 grams of AlCl3 because once I get to making 671 grams, I'm done, I'm out. So I just think of this as my reaction is running over time. I start out with 0 grams of AlCl3. And then at some point in time, I've made 600, 650, 671. And once I make that 671 grams of AlCl3, I'm out of chlorine. And so I stop, I'm done. And so chlorine is my limiting reactant. So in practice, all you need to do is pick each of your reactants separately. With 535 grams of chlorine and an infinite amount of aluminum, I could make 671 grams. With 255 grams of aluminum and an infinite amount of chlorine, I could make 1,260 grams of AlCl3, but I don't have an infinite amount of chlorine. I only have enough chlorine to make 671 grams. So chlorine is limiting and aluminum is in excess. Questions? Does this make sense?
So to solve this type of problem, you need to like run through both scenarios if we have an infinite amount of aluminum or chlorine.
Yep, exactly.
All right.
So here's another example. So I have 3A plus 2B going to C. If I have 10 moles of A and 8 moles of B, which of those reactants is limiting? And then the other question I want you to think about is, what if I had given you these amounts, this 10 moles of A and 8 moles of B in grams, what would you have needed to do? So I'm going to send you into your groups to chat about this. I'll pull you back in like 5 minutes, so 11:35.
Wait, we just have to talk about which is the limiting factor in this one.
Yep, so answer both of these questions, which is limiting, and then what would change if I had given you, instead of moles of A, grams of A and grams of B.
Okay.
Okay, so just to see how we did, I just started a poll. So which do you think is limiting, A or B? Okay, so most people think that A is limiting. So let's go through it. So if I have 10 moles of A and I forget all about B, how many moles of C can I make if I use up all of that A? If I have 10 moles of A, I can make 1 mole of C for every 3 moles of A, so I can make 3.33 moles of C. If I have 8 moles of B and forget all about A, I can make 1 mole of C for every 2 moles of B, so I could make 4 moles of C. But before I make 4 moles of C, I have to make 3.33 moles of C. And I can't get past 3.33 moles of C because I've run out of A. So that means that A is limiting. Does this make sense? Okay. And then can somebody tell me what they would need to do if I gave these amounts in grams? You can unmute or send something to the chat. What would change about this problem?
The notation, maybe. And it's pretty much it. And the amount of grams, right?
Say that again?
No. The notation, like instead of moles, you have grams.
Yeah, so that would change. But also you would need to convert to moles. So a couple people put that in the chat. So yes, you would have it in grams, but you would, in order to use those stoichiometric coefficients, you need to use moles. So I can't say 1 gram of C per 3 grams of A. I can only do that in moles. So you guys are exactly right in the chat. You need to convert to moles, and to do that, you would need the molar mass. So if I told you A is CO2 and B is H2O, you should be able to figure out the molar mass using the periodic table. In this case, since you don't know what A and B are, I would need to give it to you. Any questions on how I did this, or what limiting reactants are, or how we can figure them out? So the last concept I want to talk about today is what's called yield. So there are a few different kinds of yield. The theoretical yield is the best that I could possibly do. If I used up absolutely all of my limiting reactant, how much C could I make? And so from our previous slide, that is 3.33. If I used up all of my limiting reactant, which is A, I can make 3.33 moles of C. That's the best I could possibly do. So in this case, if I have 5 moles of A and 2 moles of B, what is my theoretical yield of C? Well, if I used up all of my A, I could make 2.5 moles of C. If I used up all of my B, I can only make 2 moles of B. So B is my limiting reactant. If I use up all of my limiting reactant, I could make 2 moles of C. So B is my limiting reactant, and my theoretical yield, the best I can possibly do, is make 2 moles of C. The actual yield is how much you actually end up making. So this you can't figure out. This is like I ran an experiment in my lab and I found that I made 1 mole of C or 1.5 moles of C. So on a test or in, when you're not in a lab, someone would have to tell you this. So in this case, I ran an experiment in my lab and I actually made 1.5 moles of C. So yield is like how much product do you have? How much did you make? And so the actual yield is how much you actually made. And then the percentage yield is just a measure of how well you did relative to the best you could have done. So it's my actual yield divided by my theoretical yield. And then to convert that fraction to a percent, we multiply by 100. So in this case, 1.5 divided by 2 is 75%. So just to repeat, my theoretical yield is what is the best that I could possibly do given the reactants that I have in front of me. The actual yield is how much I actually ended up making. So that would need to be given to you. Someone needs to tell you. And then the percentage yield is the actual divided by my theoretical times 100.
Wait, so the theoretical yield is just the output of the limiting reactant?
Yep. So if it's the best I could possibly do, and the best I could possibly do is using up all of my limiting reactant, how much product could I make? Does that make sense?
Yeah, thank you.
Okay. Did I see a hand, a different hand, or?
Yeah, I was gonna ask the same thing. It's like, is the limiting reactant the same as the percentage yield, or no, the theoretical yield?
So the amount of product that I could make if I used up all of my limiting reactant is the theoretical yield. So back on this slide, yeah, exactly. So someone asked this in the chat. On this slide, my theoretical yield is 3.33 moles of C. So I used up all of my limiting reactant, my 10 moles of A, and I made 3.33 moles of C. So my theoretical yield is 3.33 moles of C. Okay. So the last practice question for the day is going back to this same reaction we've been using before. I have 535 grams of chlorine and 255 grams of aluminum. I just want to make sure you notice that those are the same numbers that we had before. So there's a lot of math that you don't need to redo because you've already done it on a previous slide. And the additional information I'm going to tell you is that I ran an experiment in the lab and I made 300 grams of AlCl3. So in your groups, I want you to figure out your percentage yield. And to do that, you're first going to need to decide what your theoretical yield is. So last breakout room question of the day. I'm going to send you in there. I'll give you until 11:50. And those of you watching this later, please pause this and practice. Okay, welcome back. So just to walk through this that I've just popped up on the screen is just the things that we figured out on the previous slides. So what I found before is that with 535 grams of chlorine, I could make 671 grams of aluminum chloride, or AlCl3. With 255 grams of aluminum, I could make 1,260 grams of product. And so once I make my 671 grams, I'm out of chlorine. Chlorine is my limiting reactant and aluminum is in excess. So none of this is new information. This is all from the previous slides. So my theoretical yield is how much product I can make if everything goes great. If I use up all of my limiting reactant, the most product I can possibly make is 671 grams of aluminum chloride. So that's my theoretical yield. I told you that in my lab, I made 300 grams of aluminum chloride. So my actual yield is 300 grams of AlCl3. And so my percentage yield is just 300 divided by 671 times 100. So my percentage yield is 44.7%. So yield is a really important concept. As you're doing practical chemistry, you really want to make as much of your product as you possibly can. You want to convert as much of your reactants to products as you can, because the products are what you want. And so yield is a really important idea, and it lets us quantify how good of a job we did. And so a lot of both chemistry and chemical engineering in particular has to do with increasing this yield. And so if these kinds of calculations are interesting, might I interest you in a chemical engineering class? This is my shameless pitch to steal you all from the College of Engineering and into the College of Chemistry. But this concept of yield is just a really important way to quantify how well we've done at converting our reactants to our products. So we would love to get our percentage yield up to 100%. Any questions on yield, theoretical, actual percentage, limiting reactants, anything we did today? Okay, so that's all we needed to cover for today. So please stay after if you have any questions. We can also talk about previous things. So on homework 7, there was still some confusion on line drawing. So happy to go over that as well. So yeah, stay after, let me know if you have any questions, and homework 8 is posted.